Hello students, welcome to lecture on study of transistors. In this lecture, actually this is first lecture. In this lecture we will see some multiple choice questions on transistors. In next lectures we will see biasing circuits, DC load line, UJT. So let us go to first basics of transistors. Now in transistor, this is semiconductor chip, and here this semiconductor tip is doped. Here it is doped with trivalent impurity. Here this region it is doped with pentavalent impurity. This region it is doped with trivalent impurity. This is one case. In second case, this is semiconductor chip like germanium or silicon. Now this region it is doped with pentavalent impurity. This region it is doped with trivalent impurity, and this region it is doped with again pentavalent impurity. So here we get one junction here and one PN junction here. Here also we get one PN junction here, and here it is one PN junction. So now here it is pentavalent, so it becomes N type, this becomes P type, and this is N type. Here it is trivalent, so this is P type, N type, P type. So it is called PNP transistor, and this is called NPN transistor. Now out of these three regions, one region it is called emitter. This middle region it is called base, and this region it is called collector. This is also emitter, base, and collector. So three terminals are taken out. One terminal it is taken out from this region, second is taken out from this region, and third is taken out from this region. Now this emitter region it is heavily doped. This base is lightly doped, while this collector region it is moderately doped. Now collector region has large size, while base region it is thin. Base region is thin. Collector has large size because it has to collect charge carriers. Now if we take PNP transistors, majority charge carriers are holes, and here majority charge carriers are electrons. Here also three terminals are taken out. So here if we see PNP transistors, we will get two junctions, and equivalent circuit is like this. This is emitter, base, collector. Here equivalent circuit is like this. Emitter, base, collector. So in NPN transistors, majority charge carriers are electrons, and here majority charge carriers are holes. Emitter, it emits charge carriers, either holes or electrons, depending on the doping. Now let us go to multiple choice questions. How many PN junctions are present in the transistor? Just we have seen there are two PN junctions. The number of depletion regions in transistor is. Now here we get one depletion region between base and emitter, second depletion region here between base and collector. So there are two depletion regions. Two depletion regions. Next one, in transistor the base is lightly doped, emitter is heavily doped. So this is for emitter, this is for collector, and this is for base. In transistor the emitter is heavily doped. Which one of the following has the largest size in transistor? So out of three regions, collector is of the largest size, base is of the smallest size. In PNP transistor, the current carriers are actually majority charge carriers. Since it is PNP transistor, majority charge carriers are holes. If it is NPN transistor, then majority charge carriers are electrons. So generally current carriers are electrons. The collector of a transistor is moderately doped. A transistor is dot operated device. Current, voltage, both voltage and current, neither current nor voltage. So suppose we take here transistor. So this is emitter, base and collector. Suppose this is PNP transistor, and we connect batteries in such a way that base emitter junction is forward bias and base collector junction is reverse bias. So here it is connected to positive of battery, this is connected to negative of battery, this is connected to negative of battery, and this is connected to positive of battery. And here we get IE, IB, and here IC, and we have here IE is equal to IB plus IC. So when we see operating of the transistor, we consider currents. So it is current operating device. It is current operating device. Now if we go to here, this is PNP transistor, this is NPN transistor. We use symbols. This is symbol for transistor. So how can we distinguish between them? So here it is a PNP transistor. This is collector, emitter and base. Collector, emitter and base. This is NPN transistor. Now since base emitter junction is forward bias, current flows from P to N. So here we show arrow. Here we show arrow. So this is symbol. For NPN transistor, this is symbol for PNP transistor. In NPN transistor, the minority carriers are. In NPN transistor, majority charge carriers are electrons. minority carriers are holes. So it is holes. Now in transistor, generally the base current is about dot dot of the emitter current. So suppose we take here transistor. So suppose this is P uh, N P N transistor. So we connect transistor. This is emitter. This is collector. This is base. So we connect in such a way that base emitter junction is forward bias and base collector junction is reverse bias. Actually like this, reverse bias. So here majority charge carriers are electrons. It is heavily doped. Here we have holes as majority and here electrons. Since collector is moderately doped, so concentration of electrons is less. So when we connect, here current flows. So here we get IE, we get here IB, we get here IC. So what happens? Electrons flow from emitter. They enter in the base. The sum of the electrons recombine with holes in base. They constitute base current, and remaining will go in N region. Remaining will go in collector region. Since base is lightly doped and thin in size, very few electrons recombine with holes in base, giving out base current, and that is about 5%. So out of total electrons that go from N region towards base and collector, only 5%, near about 5% recombine with holes in base region and give out base current. So it is 5%. A NPN transistor conducts when? Now we know for conduction of transistors, base emitter junction is forward bias. And base collector junction is reverse bias. Now it is NPN transistor. So we have symbol for NPN transistor. This is symbol. Now this is emitter, this is collector, this is base. So here, since base emitter junction is forward bias, this is NPN. So base is connected to positive of battery, emitter is connected to negative of battery. And here we take generally output in the collector circuit. Now collector emitter junction is collector, base junction is reverse bias. So this junction is reverse bias. This junction is forward bias. Now for forward bias of PN junction, here base must be at higher potential than emitter. Base is at positive potential, emitter is at negative potential. Now base is at positive potential, base emitter junction, base collector junction is reverse bias. So collector must be at higher potential than base. So suppose we take here diode. This is P, this is N. Now this end of diode, suppose is at positive potential. This is also at positive potential. This is forward bias when this is 5 volt, this is 2 volt plus. means P is at higher potential than N, then it is forward bias. So here collector must be at higher potential, means it must be more positive than base. So here we have alternatives. Both emitter and collector are positive with respect to the base. Both emitter and collector are negative with respect to the base. No. Collector is positive and the emitter is negative with respect to the base. This one is correct. This one is correct. And last, collector and the emitter are at the same potential as the base. So this is not correct. This is not correct. Collector is positive and the emitter is negative with respect to the base. So then and then NPN transistor will conduct. Now next one, in common emitter configuration, the input impedance of transistor is. Now here we have seen this is common emitter configuration. If we vary this VBE, so if we plot graph of VBE versus IE, you will get like this, or IC, you will get like this. So IE, so you will get like this. This is forward bias characteristic of this base emitter junction, and you can find here resistance by taking slope here. So for a very small change in base emitter voltage, there is large change in current. So here resistance, that is delta VBE upon delta I. So this is low. This is low. Resistance is low. Resistance is low because the junction is forward bias. Junction is forward bias. Now next one, most of the majority charge carriers from the emitter. What happens? Here actually we consider IB, base current. Now here most of the majority charge carriers from the emitter recombine in the emitter, recombine in the base, pass through the base region to the collector, pass through the base to the source. Just we have seen here. Here, whatever charge carriers from emitter, they enter in the base. Few of them recombine with holes in base, and remaining will go in collector region to recombine. Very few recombine with base. Most of them are passed through base to the collector. So what happens here? Pass through the base region to the collector. This one is correct. The most commonly used transistor configuration is, there are three configurations. Common emitter, means emitter is common between input and output. Base is common between input and output. Collector is common between input and output. These are three configurations. Out of that, most commonly used is common emitter configuration. Now in transistor, the relation between three currents is, that is equal to IE. Emitter current is equal to collector current plus base current. This is IE is equal to IC plus IB. Now the transistor amplification factor alpha is. So suppose we have common base configuration. Common base configuration. So I will take here transistor. This is NPN transistor, emitter, base, collector, base. Now here this is NPN. So this one is connected to positive, this one is connected to negative, and we apply signal here. And then here some resistance across we take output. So here we have IC, IB, IE. Plus minus. Now for this junction to be reverse bias, collector must be at higher potential than base. So what happens here? Due to input, IE changes, and due to that IC changes, and we get output here, V0. Now here current amplification factor, it is defined as IC upon IE, or change in collector current or output current upon change in input current. Now we know IC plus IB is equal to IE, but base current is very small. So we have IE, it is approximately equal to IC. IE is greater than IC, but very small difference. So here alpha is defined as this. Alpha is defined as this. And generally this alpha, it is less than 1. Less than 1. Generally it is less than 1. The transistor amplification factor beta is. Suppose we take common emitter configuration. So here this is common emitter configuration for NPN transistor. This is NPN collector base emitter. Here we give signal. Base emitter junction is forward bias, collector base junction is reverse bias, and we take output here. So here amplification factor is given as IC upon IP. So when we change input, input current changes. Due to that, output current also changes. So beta is equal to IC upon IP, or you can take delta IC upon delta IP. And this beta, since IC it is in milliampere, IB it is in microampere, so this beta it is greater than 1. Greater than 1. So the value of alpha of a transistor is less than 1. The value of beta of transistor is greater than 1. The relation between current amplification factor beta and alpha is. Now we know IE is equal to IC plus IP. What is beta? Beta is IC upon IP. And alpha is IC upon IE. So if we take here beta it is IC upon, now IB, we can take IB, that is IE minus IC. So I can take IC upon IC You can take common IE. So here 1 minus IC upon IE. Now we know IC upon IE is alpha. So alpha upon 1 minus alpha. This is beta. This is beta. So alpha upon 1 minus alpha. So C is correct. C is correct. Now in common base configuration, IC is equal to alpha IE plus dash dash dash. So in common base configuration, we have seen here. This is common base configuration. So you can take NPN transistor, you can take PNP transistor. VBE plus minus plus minus. This is collector, emitter, base. We have here IC, we have here IB, and here we have IE. And we know that is IE is equal to IC plus IB. And we know alpha is equal to IC upon IE. So IC is equal to alpha times IE. But what happens here? Suppose emitter is open. Emitter is open. So what happens? Still there is some current flowing through base and collector. And that current is called ICBO. And this current, it is called collector base current when emitter is open. So emitter is open means we make here, we disconnect this. Still we get some current through base and collector, that is ICBO, and this current it is due to minority charge carriers. Minority carriers. So though base collector junction is reverse bias, it is forward bias for minority carriers, because it is reverse bias for majority carriers. So that current we get. So IC, it is I alpha E plus ICBO, that is collector base current when emitter is open. So here C. Now next one, the output impedance of a transistor circuit is. Now here input we take between base and emitter, that is forward bias, and output we take generally in collector circuit, and collector base junction is reverse bias, so generally output impedance is high. In a transistor, IC is equal to 100 milliampere and IE is equal to 100.2 milliampere. The value of beta is. Now what is beta? Beta is IC upon IB, or we can write IC upon, now IE is equal to IC plus IB, so IB is equal to IE minus IC. So I can write here IE minus IC. So beta is equal to IC is 100 milliampere divided by 100.2 minus 100. So we'll get this as 100 upon 0.2. So it is 1000 upon 2. So beta is equal to 500. So here second one is correct. Beta is 500. Now next one, for a transistor, if beta is equal to 100 and collector current is 100 milliampere, then IE is, that is emitter current is. So here beta is given, we have to find IE. So IE is equal to IC plus IP. And we know beta is equal to IC upon IP. So what is IB? IB is equal to IC upon beta. So IE is equal to IC plus IC upon beta. So I can write here IC 1 plus 1 upon beta. So it is IC into 1 plus beta upon beta. Now IC is 100 milliampere into 1 plus 100 upon 100. So it is 101. 100 will get cancelled. Milliampere. So here 101 milliampere. The input impedance of transistor connected dot dot arrangement is the highest. Actually, it is common collector arrangement in which input impedance is the highest as compared to common emitter and common base. Common emitter and common base. Now let us consider next question. In saturation region of output characteristics of common base configuration, both BE and BC junctions are reverse biased. Both BE and BC junctions are forward biased. BE is forward biased and BC junction is reverse biased. BE is reverse biased and BC junction is forward biased. Now here, first we will see common base output characteristic circuit. So here we will take transistor. I have taken here NPN transistor. For biasing, we will take two batteries. So this is first battery, and here it is rheostat. And here I have second battery, and here corresponding rheostat to make variable source. Now here base is common. Base is common. And now since it is NPN transistor, collector is connected to negative. So we have here milliammeter plus minus. We have to measure collector current also. Now collector is connected to positive of battery. So here plus minus. So we get here IE. We get here IC and IP. Now using this voltage, we make junction, base emitter junction, forward bias and collector emitter current flows. And due to voltage between base and collector, we make that junction reverse bias. This is also milliammeter. Now, to study output characteristic, we take input constant. So here, this is output characteristic. So we plot graph between VCB and IC. Here 0, 0. Now I can take 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt, and so on. And current it is in milliampere IC. First, by using this rheostat, we make IE 0, and then we vary this one. And we change VCB from 0 to some higher volt, and we go on measuring IC. So we get graph like this. For IE is equal to 0 milliampere. Then we change IE to some higher value, keep it constant, go on changing VCB, measure IC. We get graph like this. So this is for IE is equal to suppose 10 milliampere. Then increase IE to some higher value. Then change VCB from 0 to higher volt, measure IC, and draw that. You will get graph like this. IE is equal to suppose 20 milliampere. Then same procedure repeat for higher values of input current. IE is equal to 30 milliampere, and here IE is equal to 40 milliampere. This is output characteristics. Now here we have three regions. So if we see here this region, we have this region like this, and this region. So this region it is called active region. This region it is called saturation region. And this region it is called cutoff region. Now in active region, transistor normally works. So here base emitter junction is forward bias and base collector junction is reverse bias. In saturation region, base emitter junction is forward bias. Base collector junction is also forward bias. In cutoff region, base emitter junction is reverse bias and base collector junction is also reverse bias. So in cutoff region, both the junctions are reverse bias. In saturation region, both the junctions are forward bias. While in active region, base emitter junction is forward bias, base collector junction is reverse bias. So here in saturation region, both junctions are forward bias. Both junctions are forward bias. In cutoff region, both base emitter junction and base collector junctions are reverse biased. In active region of output characteristics of common base configuration, in active region, base emitter junction is forward bias and base collector junction is reverse bias. So this one is correct. This one is correct. Now next one, a change of 250 millivolt in base emitter voltage causes a change of 125 microampere in the base current. The input resistance of the transistor is, means here we have suppose common emitter configuration. Now here we give some signal here, and between these two junctions we have VBE, and we get IB here, and we have here IE. Now input current is IB and it flows due to VBE. So what is resistance? Input resistance, that is delta VBE upon delta IB. Now what happens here? There is change in base emitter voltage, that is 250 millivolt, and there is change in base current, that is 125 microampere. So what happens here? So here we get 2 millivolt upon microampere. So 2 into 10 raised to minus 3 volt upon 10 raised to minus 6 ampere. So we get here, this is 2 into 10 raised to 3 volt per ampere, that is ohm. So it is 2 kilo ohm. So we get here 2 kilo ohm. Now next one, in common emitter configuration of transistor, the change in collector current is 2 milliampere for change in base current of 10 microampere. What is the current amplification factor? Now here current amplification factor beta is equal to, for the same circuit, it is delta IC upon delta IB. Now here change in collector current is 2 milliampere and here it is 10 microampere. So here 2 milliampere means 2 into 10 raised to minus 3, 10 into 10 raised to minus 6. So 2 by 10 into 10 raised to 3. So here we get 2 into 10 raised to 2, that is 200. So it is 200. That is 200. Now next one, if a transistor has beta is equal to 250, IB is equal to 2 microampere, then the collector current IC will be equal to. Now we know beta is equal to IC upon IB. So IC is equal to beta times IB. Beta is 250. IB is 20 microampere, means 20 into 10 raised to minus 6. So we get here 5000 into 10 raised to minus 6 ampere. So 5 into 10 raised to minus 3 ampere. So it is 5 milliampere. So this one is correct. Now next one, for a transistor shown in figure, the voltage drop across 2 kilo ohm resistance is 1 volt. If beta is equal to 50, what is the current? So here voltage drop is 1 volt across 2 kilo ohm resistance. So I can find IC because this current will flow through corrector. So IC is equal to what? 1 volt divided by 2 kilo ohm means 1 half into 10 raised to 3. So 0.5 into 10 raised to minus 3. So it is 0.5 milliampere. 0.5 milliampere, that is collector current. Now beta is equal to IC upon IB. So IB is equal to IC upon beta. So we get here IC is 0.5 into 10 raised to minus 3 divided by 50. So we get here, if we divide this, we will get this as 10 into 10 raised to minus 6 ampere, that is IB. So it is 10 microampere. So this first one is correct. First one is correct. So thanks very much. So in next lecture, we will cover some additional multiple choice questions on transistors like biasing circuits and input output characteristics of transistors. So thank you very much again. If you have any problem, you can ask me always.